Chapter 11 is called Causes of Change. It is on thermodynamics. Chapter 11, Section 1 begins with some basic principles of thermodynamics. One is that nature is going to favor reactions that proceed toward a lower energy and greater disorder. So lower energy would give the more stability, and then by disorder we're talking about the movement of particles or entropy, which we'll discuss a little bit later in this chapter. It also reviews what heat and temperature are. Heat is the total kinetic energy of a sample of particles, so it's telling us a quantity of thermal energy, so it would be measured in joules or kilojoules. Temperature is going to be an average of that kinetic energy of the sample of particles, so it's essentially telling us how intense our heat is. And we will measure temperature in either degrees Celsius or in Kelvin. Remember, if you take Celsius and add 273, that will give you Kelvin. A calorimeter is a piece of equipment that can measure the amount of heat either absorbed or released during a reaction. Remember, exothermic reactions are releasing energy, and endothermic are absorbing energy. This is what a couple of them look like. They can be kind of more complex, like this metal one here, or something as simple as a couple styrofoam cups with a lid. And we'll use these in a lab when we test the specific heat capacities of metals. We'll put the hot metal into the cup, we'll measure the temperature change, and that will help to find the specific heat capacity of those particular metals. Specific heat capacity, which is symbolized by a C and a subscript P, is the amount of heat that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So the units are going to be joules per gram degree Celsius. So a joule for every gram and degree Celsius. Water's specific heat capacity is always 4.18 joules per gram degree Celsius, and that is a value that you will need to remember throughout this whole chapter. Specific heats are kind of like densities in the fact that they're unique to specific elements. So there's a table in your book that can give you some different values of, or some different specific heats of various components, different substances. One of the equations that we're going to be using that has specific heat capacity in it is this one here, Q equals Cp m delta T. So Q is going to be heat or thermal energy. So that's going to be in joules or kilojoules. Cp is our specific heat capacity in joules per gram degree Celsius. M is mass in grams, since that's what our mass units are in the specific heat. And then delta T is going to be the temperature change, so the final temperature minus the initial temperature. And this will be in degrees Celsius. Here's an example of a specific heat problem. So this one is asking us how many joules are needed to raise the temperature of 300 grams of aluminum from 20 to 70 degrees Celsius if the specific heat of aluminum is 0.902 joules per gram degrees Celsius. So the first thing you always do is write out the equation. We'll always do equation, substitute, and solve. So for this one, we are using Q equals Cp m delta T. We're looking for how many joules, so we're solving for Q. We were given specific heat, we were given mass, and we were given the temperature change. So we just plug in those values. This is my specific heat, this was my mass, and then the final temperature was 70. And I'm going to subtract the initial temperature of 20 from that to get my delta T value. And with that, then your Celsius units will cancel, your grams units will cancel, and all that will be left over are joules. The law of heat exchange basically tells us that heat lost is gained by something else. So heat will always flow from hot to cold. Your book talks about the example of holding a snowball in your hand. The heat will transfer from your hand to the snowball to help to melt that snowball, and then your hand will feel more cold because the heat has left it. It doesn't suck the cold from the snowball into your hand. It will always flow from hot to cold. And any sort of heat that's lost by one substance has to be gained by something else. It's conserved. And as I mentioned earlier, we're doing a lab that will be measuring specific heat capacities of a metal, and we'll heat those metals up and then put it in calorimeter water, so that heat will be gained by the water, and we'll measure that temperature change with our calorimeter. So here's a heat exchange problem. It says to find the specific heat of 100 grams of an unknown metal when it's removed from water at 100 degrees Celsius and placed in 200 grams of water at 20 degrees Celsius. The final temperature of the mixture is 23.5 degrees Celsius. So heat exchange problems will always have information about a metal and about water. So these are probably the biggest problems that we will do. Now the equation that you will want to write down is CPm delta T equals CPm delta T. So essentially that's Q equals Q. So the Q of the metal is going to be equal to Q of the water. Whatever heat we have in our metal will be gained by the water. And that's why we can plug in our specific heat capacity equation here. So all the metal information needs to go on one side of the problem and all the water information needs to go on the other side of the problem. So then we're just going to plug in our values and solve it. So over here on the left side of our equation, we're solving for the specific heat capacity of the metal. We were told we had 100 grams of it. And this is where it's a little tricky with our delta T. Instead of being final minus initial, it's going to be initial minus final. And that's only for the metal side of this equation, and only in this type of problem will the initial be before the final. You basically just need to make sure that you have a positive value here. And then on the right side of our equation was all the water information. So specific heat capacity of water is always 4.18 joules per gram degree Celsius. We were told that we had 200 milliliters of water, which is 200 grams of water. And then the final temperature of the system minus the initial temperature of the water. And plug all that into our calculator and we get 3.82 joules per gram degree Celsius. Okay, then we have the ability, since this was an unknown metal, we could look up this value in a table of specific heat capacities and it could tell us which metal this would be. Another type of problem is very similar to just specific heat capacity, but it's molar heat capacity. So the only thing that's really different here are the units. The symbol is C instead of Cp, and it's just the heat required to increase the temperature of 1 mole of a substance by 1 Kelvin. So instead of grams and degrees Celsius, we're using moles and Kelvin. So the units are joules per Kelvin mole, and again, these are values that are listed in the book as well. Our equation that we're using is Q equals NC delta T, so Q is still heat. N is moles instead of grams, which would be M or mass. And then C is our molar heat capacity, and then delta T is still our final minus our initial temperatures. So here's what a molar heat capacity problem would look like. It says if the molar heat capacity of water is 76 joules per Kelvin mole, calculate the amount of heat energy needed to raise the temperature of 90 grams of water from 35 to 45 degrees Celsius. So as soon as we see this C, we know what our equation is. We need to write out Q equals NC delta T. We were given C, we were given our temperature change, and we were given grams here. In this equation, we need moles. So since we know it's water, we can use the molar mass of water to convert from grams into moles, which is what I've done here. So this is taking the 90 grams of water, using its molar mass from the periodic table to convert it into moles, and then putting in the rest of the values for the remaining part of my equation here. Now, another thing that you can do is with this type of problem, you can see our mole units will cancel, and then our molar heat capacity is in Kelvin, and our temperature here I left in Celsius. Now that's possible to do because Celsius and Kelvin temperature degree signs are the same sizes. So if I were to convert both of these values to Kelvin, I would get 318 Kelvin and 308 Kelvin. That would still give me a 10-degree difference. 45 minus 35 would be a 10-degree difference. So anytime you're doing a subtraction problem like that, you don't necessarily have to convert from Celsius to Kelvin. If you're doing an individual temperature, then you definitely need to add the 273 and convert it into Kelvin.